Okay, we're grading homework, and then we're going to quickly go over to our notes. And I think I have a quick summary page that you probably did. You possibly did with the video 2 Fridays ago. But it's okay. It'll still be a good review as far as all of section 4.5. Because even though we don't need it to start section 4.6, we do need it to finish section 4.6. So that prior knowledge from this section. So let's go ahead and finish grading homework, and then we'll do that quick summary before we do questions. You guys have already been able to look at 4, 12, and 18. Number 20, we just had that horizontal shift. I think there was a typo, but it's okay. It was an even. You guys couldn't check it anyway. But it was pi units to the left. I don't know what the F was there for, but pi units to the left. Number 34 was a bit more intense. I think they were actually asking you guys to do, let me try to zoom in. There we go. To do a couple different graphs and then like compare them to each other, which was a little bit weird, but if you took them one at a time, let's check it. This one has an amplitude of 2, so this is the guy that's the stretched one. I think his period was pi. If you guys figured that one out by just plugging into the formula, you can see like a few different characteristics. They go through and actually write out each of the 5 key points. And it was a cosine curve, and remember, cosine curves, those are the guys that start at the top, middle, bottom, middle, top. So you don't have to necessarily write them all out, but you should be able to see these locations on your graph. Does that make sense? They're making like a big old table about it and making a big deal. I just need to be able to see that you know where to put those 5 key points. But that was this guy. He goes to that taller one. And then you were also supposed to graph this little dude who wasn't stretched, so he was the guy going up 1, down 1, but he did have a negative, so he was vertically flipped. So he's that smaller guy. You might have done them separately, you might have done them together. But the relationship between each other isn't looking at like a normal cosine curve. You weren't going all the way back to this dude. Instead, you were relating them to each other and how they're different. And so this one does have that vertical flip. This guy does have an amplitude of 2, whereas this one only has 1. So technically you could say that this is 2 times bigger than that one, or a vertical stretch of 2. Or they put it that this guy is a vertical shrink of 1/2 of that one. It's kind of awkward, but they are doing the comparison this direction instead. So technically compared to him, he was a vertical shrink by 1/2, and he was a vertical flip. And his period is twice as short. Or 2 cycles of this guy will be in 1 cycle of that. And you can kind of tell a few of those things from the graph. That this guy has 2 cycles, whereas this one just has 1. Different ways of putting it. They went ahead and made it all like super official and wrote it all out, but you don't necessarily have to put it exactly the way they did. And what's more important for me, realistically, is just for you guys to be able to get these graphs. Comparison is good in other applications, but okay, this guy's more normal. And he actually only had one thing going on. He just had a horizontal shrink by 4. Everything else was still the same as far as up 1, down 1, starting in the middle, and then having your 5 key points. But instead of finishing at 2 pi, he should have finished at pi over 2. So everything was shrunk way down. So you have pi over 2 being that final point, pi over 4 being there. If you had labeled it, this would have been pi over 8 and 3 pi over 8. And they wrote it all out again. But once again, you could have just shown me those points with clearly shown units on your x-axis. Calculator, what? Nice. And it's still kind of complicated in your calculator because sometimes, if you guys notice, actually all the time, when you hit the sign button, there's the automatic parenthesis. And so if it's written like this, it's easy. It's like, okay, whatever, parenthesis, type it all out. But if it was written like, that one wouldn't have been as confusing. Are there any of those ones with the B on the outside? We haven't seen any ones that are too bad. If the B was on the outside, you guys might get a little confused by hitting that sign button and then having that automatic parenthesis. That you can always like type something, put another parenthesis if you ever needed to. That's okay also. If you were in degree mode, this would have looked all sorts of crazy. Versus radian mode, maybe you didn't notice. But a quick heads up, there is a cool zoom that we didn't talk about, I don't think very much in our Precalc graphing handbook called Zoom Trig. That lets you go between, hey, if it's radians, I'll make it appropriate, or if it's degrees, I'll make it appropriate. So when you put it in Zoom Trig, it's one of those Zoom standards, Zoom Max, Zoom Min, Zoom Fit. Zoom Trig says, hey, I'll consider this and I'll make it appropriate. So if you ever have something weird with Trig, maybe try the Zoom Trig button. Because some of you might have gotten like a weird straight line or something like that. Yeah, someone did? Yeah, Zoom Trig should make it all better. Okay. If you drew like some weird line, it was probably that you just needed to kind of reset your window. Ooh, this one was going backwards. How did you guys do on 76? Did you see that shift? And they told you cosine, so you kind of had to make it like that. You could have made it a sine curve, but you would have had to have like done something awkwardly in the middle-ish. Cosine, you can start at the bottom or start at the top. So what did they end up making it? They made it as y equals negative cosine of x minus 3, because they saw that, let's see, that's sine curve, not cosine curve. Here's normal cosine. They saw that it shifted down 1, 2, 3, 4. I thought it shifted down 5. Why did they only shift it down 3? 1, 2, 3, 4, 5. Why is it minus 3 and not minus 5? It's from because it's flipped and then shifted, right? Do you see the negative in front? So then this isn't the one I should be looking at. Wouldn't it be this one? Does that make sense? So look at it flipped and then say, oh, the bottom of the curve went down 1, 2, 3. Okay. So they said flip it and then go down 3. There are other ways you could have written it. You could have also done something like y equals normal cosine of x minus pi minus 3. Now, technically they made it so you couldn't because they didn't allow you something on the inside of cosine. But why does this match up with the exact same curve? What is this saying to do to a cosine curve? Pi to the right, because it's opposite what I think, and, okay, so I would have started with this one, and I would have gone pi to the right, and then I would have gone 1, 2, 3. Got it. So there are different ways of writing the exact same trig function, which is a little bit confusing until we get to chapter 5, but I don't think we're going to do that until after. Sadly. But that's okay. Is this the end? Yeah. Okay, get ready your questions. Here's 82, 86, and 90. Get ready your questions, but we're going to go ahead and hop over, do a quick summary of all the sinusoidals. Wait, who has a sinusoidal shape? Sines and cosine. And sines and cosines are called sinusoidal waves, right? So we'll do a quick recap of all the different transformations. Then I'll come back and see where you guys got stuck. Oh, no, I guess not. Sometimes you pull this out first, and so it would have looked a little bit weird if you had tried it in your calculator. But I think you're going backwards on this one. Nikki, what's that?
What does it mean by in the interval negative? Oh, does it?
Oh, it's just saying that specifically this graph was only from here to here.
Because when I graphed it, it just showed me 2 straight lines, like negative 1.
It's your Zoom trig again. Now this one is supposed to be a straight line, so you were okay on that one.
Yeah.
But since your mode was weird, just think of it this way. In degrees, it would take 360 and negative 360. So if you were like in a Zoom standard 10 by 10, you only saw one little piece of this. Does that make sense? Because it's been like stretched way out.
Yeah.
But if you do radians, where it's like, oh, I don't mind little numbers, no big deal. Like you can actually see the curve. So that's what's going on, and that's why you need that Zoom trig to be like radians. Just kidding. Bring it all in. Or degrees. Just kidding. Make it really big. And then I think the point of this one was to use the intersections, wasn't it? And if you actually found your intersections, or maybe just using like logic. Oh, that's great. Let's move it all over. You would have gotten decimals. Remember, your calculator doesn't do pi and whatnot. Well, that's awkward. Everything's now. Okay, well, that's fine. Your decimals would have been 3.141 by 926. Hopefully would have seen that's high, or negative 3.1. Okay, so, quick recap. Did you guys do this page with me on Friday? Oops, wrong one. This one, the big summary page? No? Okay, so if you want to, you can open up your notes to a big summary page. Or if you want, you can just listen. It's totally fine. All the information is in your notes already, at least it should be. This is just one grand old big sinusoidal wave summary. Can you see the sines or cosines? And then have those questions ready for us to peek at. But this is what I was meaning if you put into your calculator, and there's a B. Remember, the calculator makes it sine parenthesis or cosine parenthesis. Don't be confused by this. You can always type it and then put another parenthesis. It's not a big deal if it was written like that. We like it written like this because it's a little bit easier to do our setup if this B has been factored out. And remember, when you factor him away, you have to divide. That's what that little C over B is for. So, let's see, who's who? Does anybody remember vertical shift, what we call that guy? He's here. Nope, not amplitude. Careful, that's the A. Sinusoidal axis, otherwise known as the middle. So we could say y equals d is the sinusoidal axis, aka the middle. So that's right down here, y equals d. And then amplitude, that's super nice and easy to remember because he's the A. Amplitude, what is that for a wave? Amp it up, right? How high, how low? So we add A to go up from D, or we subtract A to go down from D. You want to think of it that way. So we could say that this is y equals D minus A, or we could say y equals D plus A, if you're wondering how they were getting some of their points that they were writing out. We could go to this guy next, but he's actually kind of the hardest dude to deal with, so let's go here. You remember who that is? Initial point. It's our horizontal shift. Where do we start? Now remember, sine. Ooh, that's going to get right in the way of my B. For sine, we start in the middle, then the top, then the middle, then the bottom, then the middle. And it goes through that way as far as our 5 key points. Where does cosine start? The top. Yeah, unless it's been flipped, then it won't start at the top, it'll start at the bottom. Sine's kind of funny because if you flip him, he starts at the same place, he just goes the opposite direction. But normal cosine that hasn't been flipped, yeah, he'll start top, middle, bottom, middle, top. So initial point for sine, that guy, for cosine, that guy, is going to be at that shift. So C over B, comma, and then it depends. For cosine, he's going to be at this, D plus A. And for sine, he's going to be at that y equals just D. But just remember middle. It kind of just naturally happens. But yeah, that little y guy will change based on whether it's a sine curve or a cosine curve, whether it's been reflected, etc. So now we have the B view. We've talked about where he starts. We've talked about where the middle of the wave, the top of the wave, the bottom of the wave. What we haven't talked about is how long for the wave. And so what's that snazzy word for how long a cycle lasts? Period. Period. And period has that snazzy formula you probably saw all over homework if you were grading 2 pi over b, or horizontal, backwards of what I think, times b means divided by b. And the normal period is 2 pi. If the normal period were something else besides 2 pi, you'd be like, fine, okay, whatever, just 1 over b times that. But for sines and cosines, for sinusoidal waves, that's the normal period. In radians, in degrees, it would be 360. But in radians, 2 pi, so I do 1 over b. And then I can kind of figure out where to put my initial point here or here. And then I can figure out how long to make it if I use my period. Then I can go ahead and portion this up into go halfway, wherever that is. Go a fourth of the way, wherever that is. Go another fourth of the way, like 3/4 of the way, go wherever that is. Now, which one am I drawing right now, theoretically, if it's just what you would naturally think? But we use that period to know, okay, where do we start? We start at that C over B. And then we go ahead and do C over B plus my period, whatever that is. And I do that portioning into halves and fourths. So that's what this down here is talking about. To find those key points to go ahead and make that proper. You have to take that initial point, add that period, and then go ahead and cut into fourths, whatever those portions are. So, homework questions. Probably going backwards is harder than going forwards for most of you, but go ahead. Is there anything that you guys need to ask me? Evens or odds? Straightforward ones or 18? Anything else? Emma? 93? Okay, anything else besides 18 and 93 going once? Going twice? Let me know if you find something else before we transition away. Number 18 was a graphing one, but he looked funny. Because he's not necessarily written exactly like that model I just showed you. But we can quickly, with a couple key steps, we can rearrange him to look like that. Keep cutting off the 2. We should just... Perfection is highly overrated, right, guys? Just kidding. Well, if it's not highly overrated, it's usually impossible. So we'll just go for that. Why would I rewrite it as... I shouldn't do that. The 0 was good, but the next part wasn't. Why am I writing a 0 plus anyway? Yeah, I'm saying to the axis, realizing where the center is, it hasn't shifted off the axis, so I can go ahead. Sorry, I'm back. I can go ahead for this one and say, hey, if there's no addition, all right, cool. 0 plus. So D is equal to 0, so I can go ahead and in my graph say, okay. But how high, how low is this guy going to go? What's my amplitude? What will come next? 2 thirds. There's my 1. And I can go ahead and cut that into thirds in. Got it. That's my 2 thirds and my negative 2 thirds. Now here's where it gets a little bit weird. What's going to be out there? Pi over. The whole thing needs to come away from the x so I can get my proper form, but who's going to go here? Initial point. Initial point says, is there anything being added or subtracted from the x? Yes or no? I missed it. Nope. So if nothing's there, what do I put? Good. So if I'm nice, I know my middle. I know my top if I wanted to think about it. I know my bottom if I wanted to think about it. I know my cosine starts top, middle, bottom, middle, top. So I know the sign or the shape, I should say. The shape of that cosine. The sign is positive, so it's a normal guy. It's not going to work. I know his initial point, because its cosine is going to be this 2, which is going to be 0, and then the maximum, which is 2 thirds, which I could actually go ahead and mark since I already know where it is. The problem is I can't finish until I think about this dude. Period. It says 2 pi. The normal period gets transformed how? By pi over 10 or 10 over pi? 1 over b is the reciprocal. Oh, that's weird. So how long is this cycle supposed to take?
What if you did the 2 pi over pi over 10?
Well, the bummer of that formula is you have to know how to do complex fractions. And so this would equal 2 pi over 1 divided by pi over 10. And you know division is multiplying by the, which would get to 22. Good to think about quantities. So you had 2 pi, which is 2 pi over 1, and then you had pi over 10. And that's how I was able to orient myself as to that. So 20 is how long? What's half of 20? Because 0 plus 20 is 20. Oh my goodness. Come on, wake up. What's half of 20? Everybody, it should be math factors. Pop out. 10. Thank you. Half of 20 is 10. Can you guys be thinking ahead to 1/4 of 20? Counting by 5s. 5, 10, 15. So I can go, hey, quarter cycles. Quarter cycles. Quarter cycles. Quarter cycles. Not what they asked for, if they asked for 1 period or 2, but we could keep on going this direction counting by 5s or that direction counting by 5s. We've got it. But that was number 18. I like writing it in my formula first, and then I've kind of oriented myself to where I know how to proceed. That's a life lesson, actually, if you think about it. But for right now, let's go check out that weird number 90 MSRI 3. Got it.
Quick question.
Yeah.
When there's like a bunch of different, like there's a really long period, how can you tell if it's sine or cosine?
Ooh, if you're looking at a graph and trying to go backwards?
Yeah.
Well, here's the problem. It can actually be either unless they force your hand. Like this one, they said make it a cosine, because I could have totally made these sines. Well, kind of, because it depends on how precise they are. For instance, I see that this is a maximum at 0, so I should do cosine because I know that precisely. Sine would be like halfway, which maybe is pi over. See what I mean?
Yeah.
So if it's one of those in-betweens, or this one, I'm like, I think sine would be at pi over 2. So I would do cosine because it starts at 0. Or, yeah, so if it's something where like the actual point is marked in the middle, then go sine. Otherwise, go with kind of what naturally flows. But you're right, you can totally make them into sines or cosines because they're both waves, right? 93 is on this page though. Is he on the next page? Oh, there he is. Hey, didn't we talk about Ferris wheels in class? Doesn't mean they're easy. If you guys are just bored and chilling, and you didn't do the homework, or you, on 93, just calc chatted it and didn't really use your brain, and you're not going to use it now, why don't you just pull out your calculator and start graphing tangents and cotangents and cosecants and secants and be like, huh, who are these dudes? Because they're the 4 guys we're supposed to be learning about in section 4.6. But for those of you that are invested and still paying attention, and still maybe awake too, those of you that are bored, grab out your calculator, randomly start graphing tangent, cotangent, cosecant, secant. You're not doing anything productive anyway. Start looking at what they're going to look like. But the rest of you guys, who is this dude? That's my D. That's my A. I'm going to totally rewrite this guy though because he's a mess. So let's make this 53 plus 50 sine of. You guys see that pi over 10 I'm pulling out? Oh, awkward. To pull him out, I have to divide. And dividing by pi over 10 is multiplying by the reciprocal. So that's going to be t minus. Looks a lot nicer than it did a second ago. But to get there kind of took a bit of, ooh, I have to pull away a pi over 10 from something that's not very natural. You can double check by distributing, but I'm right. Period says 2 pi over, or maybe some of you are starting to realize the reciprocal's a little bit easier on your brains. The reciprocal of b. But 2 pi over b, Nathan, you're right, it's a formula. Some people memorize it. Amplitude, there's that 50, which means did anybody realize that this was a ride that was technically, the wheel was 3 feet off the ground? And then he had a diameter of 50? Because it started at 53. And you didn't want like the poor little people here to be hitting the ground when they came around, and usually that little platform. That's a tiny platform. But anyway, 3 feet off the ground, and then 50 was the diameter both directions. So that's what it tells you about the ride. And then, to graph it, I would just do that zoom trig, and hopefully you'd be able to see your graph that would have started at 5, would have gone to, wait, why is it going to 25? Yeah. So I have to shift it to the right 5, and then it goes 20 after that for one full cycle. It's a sine curve, which means it has that snazzy middle, bottom middle, starting at 53, going up to 103, and coming down to 3. And there's my middle, let's see, 5, 10, 15. That one's easy because that 20 divided by 4 is just going by 5s. Does anybody realize why it's here at 5? Where would you get in the Ferris wheel? Would you get in the middle? Or would you get in the bottom? Yeah, you would get in the bottom, and so the ride has already been going like 5 seconds when you reach the middle, which means you got in if you were to keep going. You got in at the bottom, and then you went up. If it was a cosine curve, they could have just done a negative cosine and started it back here at 0. In answering Emma, like your earlier question. Is that Zoom trig working out if anybody's checked it because your calculators are being weird in homework?
It's doing like weird numbers.
Oh, really?
Yeah. I like X is equal to 5. Let me see. Yeah, I didn't put it down. It's 50 times 7. Yeah, sure. So in parentheses, or 10 times X inside.
Now check it. You want to be in radian mode. Sorry, I probably should have said that earlier. Some of you are messed up because you're in degree mode. And for this one, especially with the pi, they're thinking that it's radians. And then also, remember, this is a T shift. Awkward, I know, but the T is kind of like a theta because it's on that theta axis. Which means when they give you this is an angle with no units. The only type of angle with no units, with no degree mark, has to be a radian. If they put minus 30 degrees, okay, I'll do degree mode, but otherwise radian. Okay, that was a little bit of a rough one. And with the Zoom, some of you guys messing up or just not realizing with degrees and radians, that threw you off a little bit. But guys, we need to talk about tangent and cotangent. I'm going to rearrange this just a little bit so we can talk about tangent and cotangent today. And then cosecant and secant tomorrow. I have some other details that we can talk about farther down the line a little bit. But right now, let's just get the basics to tangent and cotangent today. Maybe even the basics to cosecant and secant. We'll talk about transformations tomorrow. Basically, looking towards the end of the semester, let me get rid of the unit circle. The unit circle is going to become important again in Chapter 4B. And Chapter 4B is what we're finishing by next. I think we're taking a quiz on it. Check out the calendar online next Wednesday. Next Tuesday or next Wednesday. And then we're able to final review whatever days are remaining. At least Thursday, Friday, maybe Wednesday, Thursday, Friday. We need to get through 4-6, 2 days, 4-7, 2 days, 4-8, I think just 1 day. And then like a homework question, make sure everything is good, / review before a quiz. I think that's next Tuesday or Wednesday. Check out your calendar. The unit circle is coming back. So I could go ahead and draw the unit circle, and that's what I just erased. But for some of us, I think the cheater chart is the wisest way for us to think about things. Square root of 3 over 3, 1 square root of 3. You're not done with this yet. 0, undefined. Where is tangent undefined? What angle is this, guys, in the cheater chart? Okay. Some of you, I know you're unit circle people. There aren't many of you, but there are a couple of you. So you're thinking of when tangent y over x is undefined, is when x is 0, which is at the 90-degree mark. So long story short, tangent doesn't exist at pi over 2, which means if I go to graph tangent and I'm at pi over 2, which actually happens quite quickly as compared to, like, I don't know, sine and cosine go all the way to 2 pi. Maybe I'll bring it in a little bit. Every time I'm at a 90, whether up 90 or down 90, so pi over 2 or 3 pi over 2, or whether I go backwards if you're thinking unit circle, or whether you go backwards like negative pi over 2, which would be over here. Tangent doesn't exist, and not only does it not exist, it has vertical asymptotes. At any of those pi over 2's, and any pi jump away from that. So pi over 2 plus 2 pi over 2 or minus 2 pi over 2. If I go pi away, because if I think my unit circle, there's a pi distance, whether or whatever direction I'm going, I'm going to have little vertical asymptotes. So I might not know much about the graph, but I do know tangent's going to have a whole lot of vertical asymptotes, which is weird. Waves just keep going. Asymptotes break everything up. Wait a minute, I don't just know that. I also know that tangent is 0 every... Wait, that's pi over 2. Who's this guy? careful. That's pi over 3, pi over 4, pi over 6. Who's this?
0.
Yeah. Ah, hey look, 0, 0. That's an easy point to remember. But tangent repeats every pi, so guess what's going to be here too? If I was to go to 2 pi, 3 pi, 4 pi, or negative pi. Okay, so tangent has all these zeros and he has all these asymptotes. Anything else? Do you guys realize that everything is pi away from itself? The zeros are pi away. The vertical asymptotes are pi away. That's weird with tangent. And actually cotangent is super similar, except cotangent, he flips this guy, right? So this guy comes from 0 over 1. This guy comes from 1 over 0. Cotangent, if I was to do that to the table, would be backwards. He'd be undefined. Square root of 3, 1, root 3 over 3. If I was to do him in the cheater chart, we don't usually do that. But if I flip 0, I actually get undefined. And if I flip undefined, I actually get 0. So cotangent is kind of backwards, because at 0, he's going to have an asymptote. And at pi over 2, he's going to have a 0. And so we can kind of follow the same pattern. All the places that guy has a 0, this guy has an asymptote. All the places that guy had an asymptote, this guy has a 0. So actually he's 0 plus pi m, which is kind of weird. Domain and range, they're super similar, because if you were to keep on going with tangent, he's actually growing here, and he's going to keep growing, because undefined is actually infinity. The reason that's why we say undefined, dividing by 0, this is a weird concept you guys probably haven't heard before. Dividing by 0 isn't so much like, oh, we have no idea, it's that it's getting closer and closer and closer to infinity, which isn't a number, so we say undefined. But the cool thing is, we kind of know what to do in a graph if it's infinity. That's easy. Got him. And he reminds me of the cubic function, kind of. He doesn't go forever left, forever right, like an x cube, but he sure does look like them held within these vertical asymptotes. Tangent is positive in the first quadrant and negative in the fourth quadrant. And once I have one cycle of him, he's just going to keep repeating and repeating and repeating and repeating. So I can talk about his domain and range, because domain, okay, well, x can't equal any of those vertical asymptotes. But the y, well, he goes forever high, forever low. So if I was doing intervals, you guys remember how to do intervals with forever low, forever high? How low does he go? Negative, careful. And then how high does he go? And cotangent's the exact same thing, it's just shifted. Well, here's a weird thing. If tangent's getting bigger here, if I was to flip bigger numbers, it's actually going to be getting smaller. There we go. For cotangent. And then wherever tangent is, well, let's just think about it as if cotangent is the reciprocal, then his graph is going to be like a vertical flip, if that helps. So they're super similar to each other. And that their domains are the exact same as in, like, hey, no vertical asymptotes. I mean, the vertical asymptotes are a little bit in different places. But still, okay, vertical asymptotes are bad, but the range is forever low, forever high. If you look at him, he actually, cotangent, has that even symmetry that we already talked about in an earlier section with all those properties in chapter 4a. This dude's an even guy, whereas this guy, if you look at him, he flips over and down. He's an odd guy. But that's tangent and cotangent. Now, if any of you guys graph the cosecants and secants, we're going to look at them tomorrow, you would have seen something really weird going on in your graph. And you would have been like, what the heck is? Until you realize it's just bouncing off the wave. Tomorrow we'll learn if you have a wave, you have a cosecant and a secant real fast. Oh, of a transformed one? We didn't do transformed. But Nikki, it's pretty easy. check it.
Okay,
I said,
Oh no,
you can.
See, my homework's all fit to the drive and I'm very can't turn it in.
Take whatever's inside.
I do. I
Take whatever.
I know.
After it gets all
Yeah, I
nasty
do
and
it,
shifted,
and it
you
just
just
won't
set it
save.
equal to and solve for it.
I am.
And you take whatever's
I
inside
am.
and set
The
it equal to
classroom.
and solve.
You.
Matthew got
Yeah. See, it's not saving. Right. Okay, yeah. Alright, take a picture.